Hey everyone, we're going to diagonalize this matrix A if possible. The approach that we're going to take is we're going to find the characteristic polynomial of A in order to find the eigenvalues, and we'll note their multiplicity. Then we'll find the eigenspaces for each of the eigenvalues, and then if that all works out, and the dimension of the eigenspace equals the multiplicity of the eigenvalue in each case, then we have a diagonalizable matrix A, and we can then write the diagonal matrix D that A is similar to, and the matrix P that gets us over there. So let's begin. A has the characteristic polynomial, which remembers the determinant of A minus lambda I. And because A is lower triangular, we're going to get 5 minus lambda squared times negative 3 minus lambda squared. We're going to set that equal to 0. And I think we can see that lambda is going to equal 5 and negative 3. Both 5 and negative 3 have multiplicity 2. So if the dimension of each of these eigenspaces is 2, then A will be diagonalizable. So first, let's find the eigenspace of, we'll just do negative 3. I guess that's going to be plus 3i, right, because minus negative 3i is going to equal, so we're going to have 2, make that a little bigger, 0, 0, 0, 0, oh, no, sorry, that's actually 8, 0, 0, 0, right, because we're adding 3, 1, 4, adding 3, negative 1, negative 2, 0, adding 3. Well, that works out pretty nicely if you take a look, right? I think we can see that this is going to give us the matrix 1, 0, 0, 0, right? When we row reduce, we get in reduced row echelon form. We're going to have these 2 rows of zeros, right? Because each of those 8s can turn into a 1. Those are going to be our 2 pivots. So we're going to wind up with 2 free variables here. So we're going to say so that x1 equals 0, x2 equals 0, x3 is going to be some free variable. We'll call it, I guess we'll call this, yeah, we'll call this S. x4 is going to equal t. And so we're going to have that the eigenspace of negative 3, which remember it's just the null space of A plus 3i, right? This is just going to be S times the vector 0, 0, 1, 0 plus t times the vector 0, 0, 0, 1 for any real numbers, for all real numbers, S and t. All right. So there you go. Now, the same sort of thing for the eigenspace of 5. So we're going to find the eigenspace for 5. A minus 5i is going to equal, so it looks like we're going to have zeros for those top 2 rows. That'll be kind of nice. And then we're going to have 1 for negative 8, 0. Because we're subtracting 5, and then it looks like negative 1, negative 2, 0, negative 8. All right. And when we do some row reduction, let's see. I'm going to do row 3 plus row 4. And I'm also going to swap row 1 with row 3. So it's going to give us 1, 4, negative 8, 0. Then we're going to have, I'm also going to swap row 2 with row 4. So we'll have here 0, 2, 0, negative 8. And I think we see that this is then going to reduce to 1, 4, negative 8, 0, 0, 1, 0, negative 4. These are going to be a bunch of zeros here. And since this is on video, you can go back and rewind this. I think we can see that if we did negative 4r1 or negative 4r2 plus r1, that'll turn into a 0. And that will turn into a positive 16, I guess. All right. So it looks like here we have that the eigenspace of 5 is going to equal the set of, what looks like it's S times, so I guess what is that? Negative 8. No, I guess that's positive 8, sorry. Positive 8, 0, 0, 0. Oh, let me make that a little bit nicer. 8, 0, 0, 0. Plus t times, what's that going to be? Negative 16, 4, 0, 0. Oh, actually, this should be a 1 right there. And that last, and actually, this should be a 0, and that should be a 1 down there. Make that a little bit clearer. Negative 16, 4, 0, 1. All right, so we have the eigenspaces. So with this knowledge, so we know that A is diagonalizable. And A is going to equal P, D, P inverse for, and now D is going to equal, so which way, we'll just, it doesn't really matter which way you write your eigenvalues, but however you write, whatever order you write them in, you have to write the eigenvectors in that same order. So we put negative 3 in the first two columns. So the eigenvectors need to then, for 3, need to be, negative 3 need to be the first two columns, right? So negative 3, first two columns. So what were the two eigenvectors? For these, it doesn't matter which way you write them. I'll just write it 0, 0, 1, 0, 0, 0, 0, 1. And then for 5, it is, was that 8, 0, 1, 0. And then it is, what is that? Negative 16, 4, 0, 1. Okay? So it turns out if you did this guy times that guy times this guy inverse, you'll get A. And we have diagonalized A because it was possible.